All right. So you accidentally throw your car keys at a 65-degree angle with a velocity of 8 meters per second from a cliff. You can see that the keys landed 28 meters from the base of the cliff. We want to know how high was the cliff. All right, so I'm going to start out with a little picture here just so we can kind of see what's going on. There's my cliff. Here are my keys. I know they don't look like keys, but nobody's perfect. All right, we got a little arrow going up this way, 8 meters per second. And we know that this angle right here is going to be 65 degrees. We know that the path of the keys will be something like this, right? They're going to make some sort of parabola and come down and land on the ground. We know that this distance right here is going to be 28 meters. All right, the keys land 28 meters from the base of the cliff. We don't know how high this cliff is, what the height of the cliff is there. All right, so we've got our picture. Let's turn it into a little table here. So we've got initial position, final position, initial velocity, final velocity, acceleration, time. We'll have those for the x and for the y directions. All right. And let's start filling things in. Let's fill in some units first. Meters, meters, meters per second. Positions are in meters, velocities are in meters per second, acceleration is meters per second squared, time is in seconds. Now there's some things that we can fill in right off the bat here, just because we know what kind of problem we're dealing with. Acceleration in the x is going to be 0. Acceleration in the y is going to be negative 9.8. Those we can fill in right away. Those will always be the same. Now we have to start looking at the problem. I like to put my initial position as 0, 0. You don't have to do that, but that's how I like to do it. I know that our horizontal distance, right, in the x direction side to side is 28 meters, so I can throw a 28 in right there. I don't know how tall the cliff is, right? Our position in the y direction tells us how tall the cliff is. That's what I'm looking for. Initial velocity, I have an initial velocity of 8 meters per second, but right now it's at an angle, which means I can't put it into either of these spots yet. I have to turn it into its components first. All right, so I'm going to leave those blank for now. Final velocities, I don't know anything about right now, and I do not know how much time it took. All right, so that's what I'm working with right now. Now, if we look at this, I know 2 things in the y direction, which doesn't give me a whole lot of help, and 1, 2, 3 things in the x direction, which also doesn't give me a lot of help. I need 4 things in order to do anything here. So I'm going to need these initial velocities. So I'm going to come down here. I'm going to draw my little velocity vector, right? It's 8 meters per second. I know the angle is 65 degrees. And I've got an x component there, and I've got a y component there. X and y. All right, my x component is going to be the velocity times the cosine of the angle. The velocity is 8 times the cosine of 65. And a second. Cosine of 65 is 0.42. All right, and then we can go ahead and multiply those out, and we'll get a velocity of 3.38 meters per second in the x direction. We go ahead and do the y then. Y is v times the sine of theta. So we'll get 8 times the sine of 65. Sine of 65 is 0.91. We multiply those out, and we'll get 7.25 meters per second for the y direction. All right. If we'll notice, x is pointing to the right, so this is going to be positive. Y is pointing up, so that is also going to be positive. So I can fill those in my table now as well. 3.38 for the x direction and 7.25 for the y direction. Now, we want to know how high the cliff is, but if we look at the y direction, we have 1, 2, 3 known values, which doesn't work, right? We need to know 4. So if we look at the y side or the x side, we have 1, 2, 3, 4 known values, so we can solve for time here, right, as a little intermediate step, so that I can have 1, 2, 3, 4 things in the y direction and can solve from there. So I'm going to go ahead and solve for time using the x direction. Now you notice I'm missing final velocity in both of them, which makes the second equation really appealing. So I'm going to use xf equals xi plus bit plus 1/2 at squared. Plug in my values here, 28 meters equals 0 plus 3.38 times t plus 1/2 times 0 times t squared. Over here, everything's multiplied by 0, so that goes away, and we get 28 equals 3.38 t. All right, so we can go ahead and divide that 3.38 over to the other side, and we'll get a time of 8.28 seconds. All right, so it took 8.28 seconds for the keys to hit the ground. Now I can use that in my table over here, and I have 1, 2, 3, 4 things for the y direction now, and I can go ahead and solve for the height of the cliff using the y direction. I'm going to use the y direction there. All right, so again, we're missing final velocity, so same equation. xf equals xi plus bit plus 1/2 at squared. Plug some stuff in here. xf we don't know, that's what we're looking for. 0 plus 7.25 times 8.28 plus 1/2 times negative 9.8 times 8.28 squared. Running out of space on the page there. Should have started over a little farther. So we've got just a little bit of math here. xf is going to equal 7.25 times 8.28 will give us something around 60.03. 1/2 times negative 9.8 times 8.28 squared will give us something around 335.9. And when we go ahead and subtract those, we get xf is equal to negative 275.9 meters. Now, does that mean that the cliff is negative meters tall? No, that tells us the keys went 279.5 meters down, right? That's why that negative sign is there before they hit the ground. So what is the height of the cliff? The height of the cliff is actually positive 275.9 meters. So there is the solution to the first one. All right, let's look at the second one here, if I can get it centered. You took a running leap off a high diving platform at an angle of 15 degrees. You were running at 2.8 meters per second, and you hit the water 2.6 seconds later. We want to know how high was the diving platform and how far from the edge of the platform did you hit the water. All right, so there's our important stuff: angle, initial velocity, time. We want to know how high, and we want to know how far. So again, I'm going to just make a little picture here. give ourselves a little bit better idea of what's going on. Here's me running off the platform, jumping at 2.8 meters per second, angle of 15 degrees. I'm going to come out, land in the water, make a little splash. There we go. And we know that this whole process takes 2.6 seconds, which is actually a really long time for a diving board. All right, so we've got our picture. Let's make our chart. XI, XF, VI, VF, A, and T in both the X direction and the Y direction. Meters, meters, meters per second, meters per second, meters per second squared, and seconds. Okay, so again, really easy. Accelerations first, 0 and negative 9.8. Time, right in there, 2.6. Start off with the initial positions at 0. Again, that's just how I like to do it. You don't necessarily have to do that, but it makes it easier for me. Positions, we don't know. This one right here, right, position in the X direction will tell us how far. This one right here, position in the Y direction, will tell us how high. All right, so X direction, how far, Y direction, how high. Initial velocity, again, we have an initial velocity, but it's at an angle, which means we're going to have to take that initial velocity and turn it into its components, its X and Y components. Final velocity, we know nothing about. We don't care about it. It doesn't help us in this problem. All right, so let's take our 2.8 meters per second at an angle of 15 degrees. There's my X component and my Y component, 15 degrees. X component is going to be velocity times the cosine of theta, just like we just did. Velocity is 2.8. Am I still on the page? Yeah. Cosine of 15 degrees. If we go ahead and do that, we get the cosine of 15, which is, I don't know that one off the top of my head, 0.97. So 2.8 times 0.97 will give us a velocity in the X direction of 2.7 meters per second. Same thing in the Y direction, right? Except that we use sine. So the sine of the angle, 2.8 times the sine of 15 gives us 2.8. The sine of 15 is 0.25, 0.26 actually. Multiply that by 2.8, and we end up with 0.72 meters per second as the velocity in the Y direction. So I can plug those in my table, 2.7 over there, 0.72 in the Y direction. And at this point, if I count, I have 1, 2, 3, 4 things in the X, 1, 2, 3, 4 things in the Y. I could solve either side right now at this point because I have enough information in my table. I think I'm going to go ahead and just solve them in the order that they're asked. So first was how high. So I'm going to solve for how high first using the Y direction. Again, we're missing final velocity, so I'm going to use the second equation. XF equals XI plus VIT plus 1/2 AT squared. XF is going to be what we're looking for. XI is 0 plus the initial velocity in the Y direction, 0.72, times the time, which is 2.6, plus 1/2 times negative 9.8 times 2.6 squared. All right. 0 goes away. 0.72 times 2.6 will give us 1.872 minus 1/2 times 9.8 times 2.6 squared will give us 33.124. We go ahead and we do that subtraction there, and we get 0.872 negative 31.252 meters. As far as decimals go, I'm not really concerned with how far we take the decimal place out. 2 or 3 places is usually good. If you like to round to 1, I'm honestly pretty okay with that too. Doesn't really matter. So we've got negative 31.252 meters. Again, is the platform negative meters tall? No, but we fall 31.252 meters when we jump off the platform, which means the platform is actually positive 31.252 meters tall. Now, second, we want to know how far away from the cliff did we land, which means we're going to have to use the x direction. So we're going to solve for how far. Go up here just because I need a little bit more space. We're going to use the x direction to do that. So we start, again, we don't have final velocity. So we're going to use xf equals xi plus vit plus 1/2 at squared. At this point, we should kind of be comfortable with the fact that this whole part, when we're using the x direction, just goes to 0. So I'm going to ignore it so I don't have to keep writing it over again. xf is going to equal 0 plus the initial velocity is 2.7 times the time was 2.6. 2.7 times 2.6 will give us, oh, I just added them. 7.2.02, sorry, meters for how far we end up from the platform. All right, so there we go. Second problem, solutions. First problem, let me get it all on the screen here. Solutions, all right.